Hello and welcome back, everybody. Today in calculus, we will be looking at work. So this is more of the physics part of calculus. So hopefully, it'll be just a little bit different change of pace, if anything. Okay. So just to begin with, let's see. We are going to define the following for us. Okay. So we're going to define that work is equal to force times distance. Now, this equation seems simple enough for the most part. And then from there, we're going to branch off into something that's a little bit more complex or a little bit more abstract, depending on how you look at it. Okay. So here in the first example right here, just to make things simple, I'm asking for how much work does it take to push a 200-pound girl 6 feet across the floor. So I want to know, like, how much energy is basically being exerted for doing something like this. Well, as we said, work is equal to force times distance. So the force is basically looking at the weight of the girl, which in this case is going to be 200 pounds. Whereas the distance that she needs to travel will be 6 feet then. So the amount of work in this case is going to be equal to 200 multiplied by 6. And the units for it will be pounds over here because she is 200 pounds. And then the distance that needs to travel will be 6 feet. So the total answer is going to be 1200. And the way we denote this will be foot pound over here, okay, to a foot pound or pound foot. I think foot pound is actually correct. So let me just kind of change that a little bit just to make the notation a little bit more appropriate. So foot pound. All right, now let's go ahead and do the same thing, but now this time we're not looking at America, but somewhere else in the rest of the world, because we don't always use pounds everywhere or feet everywhere. So in the second example, it says how much work is required to drag a 90 kilograms little boy across 5 meters. So the idea here is exactly the same thing, but we are going to do a small little modification. The 90 kilograms over here, this is what is known as mass. And when it comes to mass, that is not the same thing as force. Force is a weight. Force is supposed to be equal to mass multiplied by acceleration. So what that means is I need to multiply my mass by some sort of acceleration. And the acceleration that we're referring to is supposed to be equal to gravity. So then that just means we have to do a small little modding, and then we'll still get our answers. So the work in this case is going to be equal to force multiplied by distance. Once again, that's our equation. But to change it, force, if you remember, is supposed to be mass times acceleration and then multiply by the distance. So now we can go ahead and put everything together. Mass, which is supposed to be 90 kilogram, and then multiplied by the acceleration, which is again is going to be gravity, is 9.8 meters per second squared, and then multiplied by the distance that's going to be traveled is going to be 5 meters. So take all those numbers and multiply it out, and that is going to be our answer then. So in this case, it comes out to be approximately 2,450, which is going to be a really weird unit because if you take a look at all those things multiplied together, there is just definitely a lot of different things to consider. When it comes to force, inside this part over here, that can be changed into something called newtons, just to make it a little bit easier. So instead of saying kilograms times meters per second squared, we just go ahead and call it newtons. And then you also have the meters right here. So then that means that the unit that we're solving for is called newtons meters. Or if you want, just so that it sounds a little better, it is also what is known as joules. Okay, so either one of those should be okay. But that's basically the simple idea behind work. You need to figure out what something weighs, or what is the mass, and then multiply it by the distance that you are going to have it traveled, for the most part. So where it gets a little bit more complicated, or how does this relate to calculus is, well, what if your force is changing? What if the weight of something is changing as you are dragging it or pushing it? So for example, maybe let's say that you have a bucket full of water and you're trying to hoist it up a building, and unfortunately that bucket is leaking, so then the amount of water is actually decreasing as you hoist it up. Or maybe the other way around. Maybe the bucket is empty, and then as you are hoisting it up, it starts to accumulate the rain that's inside the bucket, and as a result, it gets heavier and heavier. So how do you deal with something like that? Well, just to give you an idea, we're going to look at something like the following. What I can do is I can say that force, hey, let's go ahead and say that that's going to be some sort of function of x, where x is supposed to be the distance at a certain time. So for example, let's say that you hoist up the bucket after a certain height, you're going to have a certain force. So we'll just go ahead and call it f of x. The distance that that small little force will have to travel is going to be called delta x, because as soon as you hoist it up, right, you hoist it up just a little bit, the force is going to change. So I want to know what is the work done on that small little slab before it starts changing the force. Well, take these two multiplied together, that's going to be the work at that instantaneous moment. So we'll go ahead and call that W for the little slab then. And you can probably see what's going to happen over here. Just like with our volume, if I want the total work, that is going to be the summation of every single one of those work slabs. So what that means is I'm going to have to take my f of x and replace it in there. And then we also have to multiply by delta x. And as soon as you, again, see the summation and also delta x, then that tells you that you're going to have to set up some sort of integral. And that is where your calculus is going to come in then. All right, so let's go ahead and look at some possible questions that deals with this situation here to see how this all works out. So first off, before we do this problem, there is something in physics called Hooke's law that we're going to have to apply here. Okay, so Hooke's law says the following: the amount of force that it takes to stretch or compress a spring x units from its natural length is proportional to x. So then that means that if you have, like, say, a spring that is going to be, let's see, like kind of like, attached to a wall over here, right? The amount of force that it takes to stretch it or compress it. So if you have this box over here, and if you want to push it towards the wall or you want to pull it away from the wall, they're saying that that force is going to be proportional to the distance that you're going to push or pull it. So hopefully that part kind of makes sense, because, the further you pull it or the further you push it, the more force it's going to be, right? So that is going to be our Hooke's law in this case. So now let's go ahead and apply Hooke's law into all of this. Here's what I want to do. I want to find the work that is required to compress a spring from its natural length of 1 feet to a length of 0.75 feet if the spring constant is supposed to be 16 feet per pounds per feet. So here, let's go ahead and apply Hooke's law. We have, again, the equation F is equal to K times X. So fortunately, in this problem, we know what the spring constant is, so that is given to us. So that's going to be our value of K. A lot of the times that's not going to be given, so we're going to have to kind of work for it. So we'll do that in just a little bit, okay? But we're going to go ahead and take this step by step. So first off, we know that the force is going to be equal to 16x in this case then, okay? What I want to do is I want to find the work required to compress the spring from its natural length of 1 feet. So that means that the distance that you're going to have to push or pull is going to be 1 feet. Now keep in mind that this is the force at any instantaneous moment. The distance that you're going to have to travel is going to be delta x, because you only want to push it a little bit before the work actually changes, or the force actually changes. So this is going to be an instant, okay, moment at x. And then the distance that it has to travel, again, is going to be delta x. So what that means is the work at that instantaneous moment, work at that instant, is going to be equal to 16x multiplied by delta x, because, again, it's force times distance. Well, if I want the total work, then that means it's going to be the summation of every single one of those instantaneous moments. So, again, that's where your integral is going to come in then. So the integral from the integral of 16x dx, and your boundaries, well, this is where that natural length and also how much you want to push or pull comes in. I want to compress it so that the length is going to be of 1 feet. So that means it's going to be from 0 to 1. And we don't deal with negative because we're looking at distance, so that applies absolute value. So it's always going to be from 0 to some positive number then. But there you go. If we can solve for that integral, then that will give me the total work that's going to be done then. So that seems like it's easy enough. So that looks like it's equal to 8x squared from 0 to 1. And then that means it's going to be equal to 8 if I plug in using FTC2. The unit for this, let's see if we can kind of keep track of it. Force, if you remember, that is going to be in terms of pounds. Distance over here, that is going to be in terms of feet. So if I'm solving for the work, we said earlier, that's going to be foot-pound. The summation of everything of those, every one of those single situation is also going to be foot-pound. So then in the conclusion, my answer is going to be in foot-pounds then, just as we said earlier, all right? So now let's go ahead and take a look at a little bit more complex example of all of this. This time I want to say, hey, what if I give, sorry about that. Let's say that if I have a force of 90 newtons is required to stretch a spring 1 meter beyond its natural length. I want to know how much work does it take for it to stretch 10 meters beyond its natural length to 15 meters beyond its natural length. All right, so once again, we're going to apply Hooke's law to this, but this time we're not given the spring constant, so then that means we have to kind of work for it. So first off, we're going to begin with the equation F is equal to K times X, where F, again, is the amount of force that it takes to push or pull X distance from its natural length. Now, in this case, we're told that the force is supposed to be 90 newtons at a distance which is supposed to be 1 meter. So what that means is I can actually make that substitution into here and then solve for what K is equal to. So that's what I'm going to go ahead and do then. So 90 is equal to K multiplied by 1. And if you're one of those people that wonder about the units, this is going to be N, and this guy right here is supposed to be M. So then that means that K is going to be equal to 90 in this case, and the units for it is going to be newtons per meter. Okay, so kind of the same deal as earlier, if you notice that it is in terms of pounds per feet over here. Okay, so now what we're going to do is we're going to go ahead and find the total work done. Now, remember, this force, which is equal to 90K, that is supposed to be the instantaneous moment, how much the force is going to be, okay? Instant force at x at the value of x. The distance that you're going to have to travel is going to be always a small little increment, which is going to be delta x. So oh, by the way, let me go ahead and write the units just so that you can kind of use something to work with. If you remember, force is in terms of newtons, so that we're going to go ahead and keep over there. The distance is in terms of meter. So if I take both of these, right, and try to find out what is the work at that instantaneous moment, then that's going to be force times distance. So that's going to be 90x multiplied by delta x. And that right there is going to be newtons meters, or if you want, you can say joules. Either one of those would be acceptable. Finally, I want to find out total work. So that means it's going to be the summation of every single one of those instantaneous moments. And once again, that's where the integral comes in. The integral of 90x dx. Now, the boundary, let's go ahead and read that part over here. It says, I want to find out how much work does it take to stretch from 10 meters beyond its natural length to 15 meters beyond the natural length. So what that means is my boundary is going to be from 10 to 15 rather than from, well, I guess another way you can do it is from 0 to 10 and then 0 to 15 and then take the difference between the two. But those properties of the area under the curve will allow me to just go ahead and write from 10 to 15, which is a lot easier to deal with. All right, so go ahead and put it all together. That is going to give us, let's see, 45x squared, and then boundaries from 0 to 15. So now we just have to go ahead and solve for that. And just to save you a little bit of time, I did it already. This is going to be equal to 5,625 newtons meters, or you can go ahead and write joules then. Okay. All right, well, there you go. Thank you so much for watching. This is part 1 of 3 of this section. So brace yourself for a little bit of a longer video in the near future. Okay, I'll talk to you later. Goodbye.